22nd of March, 1975, Browns Ferry Nuclear Plant, Alabama. A maintenance log shows routine leak testing scheduled for 12:30 that afternoon. In the cable spreading room, thousands of conductors route through penetration seals, polyurethane foam wrapped around cables from Units 1 and 2. The method is standard. A candle held near the seal, watching for flame movement to detect air leaks. No regulation prohibits it. The Tennessee Valley Authority's first nuclear complex, 3 General Electric boiling water reactors, the most powerful station in the world at that time. Design documents emphasize redundancy, independent protection channels, multiple emergency cooling trains, separate power supplies. The likelihood of one event affecting both units considered extremely low. At 12:37, the candle ignites material at penetration 5. Workers believe the flame is extinguished. They do not yet know that this single spark will cascade through 2 reactors and rewrite every fire protection standard in American nuclear history. January through March of 1975, Browns Ferry Nuclear Plant sits on the north bank of Wheeler Reservoir in northern Alabama. A Tennessee Valley Authority systems engineer reviews standard operational procedures in the lead-up to spring maintenance activities. The station comprises 3 General Electric boiling water reactors, Mark IV design, each rated at 1,065 megawatts electric. Browns Ferry is TVA's first nuclear facility and among the most powerful generating complexes in the United States. Design assumptions emphasized redundancy at every level. Each unit contained multiple reactor protection system channels, redundant emergency core cooling system trains, and independent electrical power supplies backed by diesel generators. According to TVA's design basis documentation, the likelihood of a single initiating event affecting both Unit 1 and Unit 2 simultaneously was considered extremely low. The plants were housed in separate reactor buildings. Control rooms were independent. Safety systems were designed to operate without reliance on each other. But one architectural feature connected them in ways not fully evaluated during construction: the cable spreading room. A single chamber beneath the control room floor where thousands of electrical conductors from both units converged, routed through common cable trays, and passed through shared penetration seals in the walls. Most instrumentation signals, control logic circuits, and safety system wiring passed through this room. It was efficient. It was logical. It reduced construction costs and simplified cable routing. R.B. Minogue chaired the Nuclear Regulatory Commission's preliminary investigating committee after the event. His report would later state, the cable configurations were not evaluated for fire propagation in shared routing pathways. The architectural decision made sense on paper. In practice, it meant that one room housed enough cable to disable 2 independent nuclear units. The Mark I containment design used a dry well surrounding the reactor vessel, connected to a large torus-shaped suppression pool below. If steam escaped the reactor, it would vent into the pool, condensing and limiting pressure buildup. The system was proven and reliable, but the instrumentation monitoring those systems, the controls operating the valves, the power supplies feeding the pumps, all of it threaded through the cable spreading room. Penetration seals were installed where cables passed through concrete walls. Their purpose was to limit air leakage between rooms, not to prevent fire spread. The seals consisted of polyurethane foam applied around cable bundles. As they entered metal sleeves embedded in the wall, the foam expanded to fill gaps. It was considered adequate for air sealing. No one had tested how it would behave under fire conditions. No regulation at the time required fire-rated barriers for cable penetrations in nuclear plants. By March of 1975, Browns Ferry had operated for nearly 2 years without incident. Unit 1 had gone critical in August of 1973. Unit 2 followed in March of 1974. Unit 3 was still under construction. The facility represented a significant achievement for TVA, proof that nuclear power could operate reliably at scale. Spring maintenance was routine. Nothing suggested the architecture itself posed a risk. 22nd of March, 1975, 12:30 in the afternoon. The cable spreading room beneath the Unit 1 and 2 control rooms. 2 electricians arrived to perform scheduled air leak testing on cable penetration seals. The maintenance log shows entry 73, 1-047. Inspection of penetrations 4, 5 and 6 for air infiltration. The task is straightforward. Hold a candle near the seal. Watch the flame. If air moves through gaps in the foam, the flame will bend or flicker. Mark any leaks for repair. The method is standard practice in 1975. Industrial facilities across the country use candles or matches for leak detection around doors, windows, duct connections and cable penetrations. It works. It is inexpensive. It requires no special equipment. TVA's internal procedures do not prohibit it. Nuclear Regulatory Commission oversight documents from this period confirm the technique was customary and acceptable for the purpose. No regulation at the time addresses open flames near polyurethane foam used for air sealing. The foam is marketed as suitable for industrial applications. It expands to fill irregular gaps. It adheres to metal and concrete. Material safety data available in the early 1970s do not emphasize combustibility as a primary concern for this application. But polyurethane chemistry matters. The foam's ignition temperature is lower than many assumed. Once ignited, it burns rapidly. The combustion produces thick black smoke filled with carbon monoxide and hydrogen cyanide. Molten foam drips as it burns, carrying fire downward into whatever materials lie below. In this case, cable bundles. The first electrician holds the candle near penetration 5. The second electrician applies fresh polyurethane foam to another location nearby. At 12:37, the candle ignites material at the edge of penetration 5. The NRC's Preliminary Investigating Committee report documents this precisely. At 12:37, the candle ignited material at penetration 5, initiating the fire. The electricians attempt to extinguish the flame. They believe they succeed. The visible flame appears to go out. What they cannot see is the smouldering combustion beginning inside the penetration sleeve, hidden within layers of foam and cable insulation. The ignition draws fire into the wall cavity where hundreds of cables pass through. Polyethylene-insulated conductors begin to heat. Insulation softens. The fire finds continuous fuel. Within minutes, the fire will no longer be a small surface ignition. It will become a cable fire, one of the most difficult types to extinguish in an industrial environment. The electricians do not yet realize what has begun. They move on to inspect the next penetration. 12:37 to 12:40 in the afternoon. Units 1 and 2 control rooms. A control room operator at Unit 1 notices a brief flicker in one of the annunciator panel lights. The panel is a wall of backlit indicators, each representing a different system or alarm condition. When something goes wrong, a pump trips, a valve fails to respond, a sensor reads out of range, the corresponding light illuminates and a tone sounds. This flicker is different. The light brightens briefly, dims, then returns to normal. A damper status indicator fails to update. The operator notes it in the log. Dampers control airflow through ventilation systems. Their position is monitored remotely through electrical circuits. A failed damper indicator is not unusual. Control circuits can fail for many reasons: a loose connection, a degraded relay, a power supply fluctuation. Isolated equipment problems occur routinely in a facility with thousands of components. The operators expect localized faults, not systemic degradation. Nothing in their training or experience suggests that a brief panel flicker represents the beginning of a multi-unit event. TVA operator testimony recorded after the incident notes. Initial indications suggested a single malfunction without broader implication. But beneath the control room floor, in the cable spreading room, circuit bundles routed through penetration 5 are beginning to short. Heat from the spreading fire softens insulation. Conductors that should remain electrically isolated come into contact. Signals degrade. Some circuits fail entirely. Others produce intermittent, unpredictable behavior. The cables passing through penetration 5 include damper control circuits, alarm system wiring, and instrument power feeds. All of these systems share common routing because they all pass through the same wall penetration on their way to equipment in the reactor building. This is the efficiency of shared cable trays. One routing path serves multiple purposes. Under normal conditions, it works perfectly. Under fire conditions, it creates cascading failures. The operators do not have fire alarms or smoke detection in the cable spreading room. The room is not considered a high-risk area. It contains no rotating equipment, no high-temperature processes, no flammable liquids. It is simply a routing space. Fire suppression systems in the room are minimal. The connection between the flickering control panel and a growing fire in the cable spreading room remains unknown. Within 5 minutes, the pattern of failures will no longer resemble isolated equipment faults. Multiple systems will begin reporting anomalies simultaneously. The operators will realize something fundamental has changed. But at 12:40, they are still troubleshooting individual indicators, unaware that the cables themselves are burning. 12:38 to 12:44 in the afternoon. Cable spreading room. Smoke begins collecting at the ceiling. The air grows hazy. One of the electricians notices the glow inside penetration 5 has intensified. What appeared extinguished minutes earlier is now clearly active again. The fire has spread deeper into the wall cavity where foam and cable insulation provide continuous fuel. The electricians expected a small surface fire, something containable with a portable extinguisher. Instead, the fire is spreading internally along pathways they cannot directly access. The penetration sleeve is a steel tube embedded in concrete. Cables pass through it in dense bundles. Foam fills the remaining space. Once fire enters this configuration, it becomes extremely difficult to reach. Cable insulation at Browns Ferry consists primarily of two materials, polyethylene and neoprene. Both are thermoplastic polymers. Polyethylene has a melting point around 110 degrees Celsius and will burn readily once ignited. Neoprene is somewhat more resistant but will degrade and combust under sustained heat. When these materials burn in a confined space, they produce intense heat and thick smoke. Oxygen is drawn into the penetration from both sides, feeding combustion. The Preliminary Investigating Committee report documents the spread pattern. Propagation occurred vertically and horizontally along cable trays. Fire does not simply burn in place, it follows fuel. At Browns Ferry, the fuel consists of thousands of cables arranged in ladder rack trays that run horizontally across the ceiling and vertically along walls. Each cable is a potential wick. As insulation burns, molten material drips onto cables below. Heat radiates to adjacent conductors. The fire spreads both upward towards ceiling trays and downward toward equipment rooms. Heat begins softening conductor sheathing throughout the affected section. When insulation melts, bare conductors come into contact with each other or with grounded metal surfaces. This causes electrical shorts, momentary or sustained current flows that should not exist. Shorts produce more heat. They also send false signals to control systems. A valve position indicator might show the valve moving when it is not. A pump status light might flicker on and off. Alarm circuits begin behaving unpredictably. Firefighters have not yet been notified. The electricians are attempting to manage what they still believe is a localized problem, but the fire is now spreading in two directions simultaneously, toward cable trays serving Unit 1 and toward trays serving Unit 2. The shared routing architecture that made construction efficient has become a pathway for fire to reach two independent reactors from a single ignition point. 12:45 to 12:52 in the afternoon. Units 1 and 2 control rooms. A second annunciator light goes dark, then a third. The pattern is no longer consistent with isolated equipment failures. Multiple independent circuits are losing signal or producing anomalous readings within the same 7-minute window. Redundant reactor protection system channels are designed to fail independently. If channel A loses power, channels B, C, and D should remain unaffected. They use separate wiring. They draw from different power supplies. The design ensures that no single electrical fault can disable the protection system. But the failures appearing at Browns Ferry are not random. They cluster. They affect systems that should have no electrical connection to each other. The reactor protection system monitors reactor conditions continuously. Neutron flux sensors measure the rate of fission reactions. Temperature sensors track coolant conditions. Pressure transmitters watch for abnormal changes. If any parameter exceeds safe limits, the system automatically inserts control rods to shut down the chain reaction. It is the most critical safety system in the plant. Its reliability depends on diverse, independent signal paths. At 12:47, control rod position indicators for several rods show intermittent signals. The indicators are electrical devices that sense whether rods are fully inserted partially withdrawn or in motion. They communicate rod position to the control room through dedicated cables. Those cables run through the cable spreading room. Some pass through or near penetration 5. An operator notes in the log, "Loss of indication for multiple rods prompted manual verification." This means sending someone to physically look at the rods and confirm their actual position. It is a backup procedure, rarely needed. The fact that it becomes necessary within 15 minutes of the initial ignition suggests the scope of circuit. Damage is already significant. Reactor building ventilation controls also begin reporting failures. Ventilation systems maintain air pressure differentials to prevent radioactive contamination from escaping the reactor building. Dampers open and close automatically based on pressure sensors and radiation monitors. Control signals for these dampers travel through the same cable trays affected by the fire. Intermittent shorts produce spurious signals that mimic abnormal conditions. A damper might appear to be closing when it is actually open. A radiation monitor might show a false alarm. Operators must now question every instrument reading. Which signals are real? Which are artifacts of circuit damage? The distinction is not always clear. Operators still lack confirmation of fire. They are inferring the root cause solely from the pattern of anomalies: multiple systems, shared routing, sudden onset, and progressive degradation. The evidence points to something affecting cable circuits in a common location. But without direct communication from the cable spreading room, they cannot yet confirm the fire's existence or its severity. 12:53 to 1 o'clock in the afternoon. Unit 2 control room. Operators record the loss of several instrumentation signals. Unit 2 is housed in a separate reactor building from Unit 1. The buildings are physically distinct structures. The reactors operate independently. Under normal conditions, an equipment problem in Unit 1 should have no effect on Unit 2, but the design included one shared space, the cable spreading room beneath both control rooms. It was an efficiency measure during construction. Rather than building two completely separate cable routing facilities, engineers created one room that served both units. Cables from Unit 1 and cables from Unit 2 converged in the same trays, passed through adjacent penetrations, and shared common support structures. The fire ignited in a penetration that served primarily Unit 1 circuits, but as flames spread along cable trays, they encountered Unit 2 conductors in the same trays. The separation between units existed in reactor buildings, containment structures, and cooling systems. It did not exist in the cable spreading room. Cable routing diagrams filed with the Nuclear Regulatory Commission show the shared pathways. Tray Section 12A carries Unit 1 instrumentation and Unit 2 control circuits. Tray Section 14B carries Unit 2 emergency cooling signals and Unit 1 ventilation controls. Penetration 7 serves both units. Penetration 9 serves both units. The architecture made sense from a construction standpoint. It violated the principle of unit independence from a safety standpoint. The Preliminary Investigating Committee documented this finding clearly. Damage to common spreading room circuits impaired multiple unit operations. This statement represents a fundamental shift in nuclear safety thinking. Before Browns Ferry, designers assumed that physical separation of reactor buildings provided adequate independence. After Browns Ferry, regulators recognized that electrical systems could create common mode failure pathways even when mechanical systems remained separate. The systems losing indication in Unit 2 include residual heat removal instrumentation, containment isolation valve status, and emergency core cooling system pump controls. These are not minor administrative systems. They are safety systems required to remove decay heat from the reactor core and maintain containment integrity. Without reliable indication, operators cannot be certain these systems will function when needed. The shift supervisor in Unit 2 makes the log entry at 12:53. Multiple indicator losses, no Unit 2 equipment failures identified locally. This means the equipment itself, the pumps, the valves, the instruments, appears to be functioning normally when inspected in the field. The failures are occurring in the electrical signals connecting that equipment to the control room. The distinction is important. If equipment were failing, operators could initiate repairs or substitutions. If signal paths are failing, operators lose the ability to monitor and control equipment remotely. Multi-unit involvement is extremely rare in the operating history of US nuclear plants before 1975. Each reactor is designed as an independent system. The probability of a single event affecting 2 units simultaneously was considered negligible during design and licensing. Browns Ferry demonstrates that electrical architecture can invalidate assumptions about unit independence. The operators now realize the event is not confined to Unit 1. The fire's location remains uncertain, but its effects are crossing unit boundaries. Both reactors are losing critical information. Both control rooms are dealing with degraded instrumentation. The scope of the event is unprecedented. 1 o'clock to 1:10 in the afternoon. Cable spreading room and access corridors. The plant fire brigade arrives with carbon dioxide extinguishers. CO2 is the standard suppression agent for electrical fires. It displaces oxygen, smothering combustion, without leaving residue that could damage equipment. It is considered safe for use near energized electrical circuits, but the firefighters face extreme conditions. Smoke density makes visibility nearly zero. Heat radiates from the cable trays. The fire is not limited to surface combustion. It has penetrated deep into cable bundles where insulation smolders and burns in oxygen-starved pockets. CO2 cannot reach these areas effectively. The nature of cable fires makes them particularly difficult to extinguish. Cables are packed tightly in trays, sometimes stacked 4 or 5 layers deep. Air gaps between cables are minimal. When insulation ignites, combustion occurs at the contact points between conductors. Extinguishing agents applied from above or the side have difficulty penetrating to the core of the bundle where fuel and heat concentrate. Carbon dioxide works by reducing oxygen concentration below the level needed to sustain combustion, typically below 15% by volume. In open areas, this is effective. In confined cable bundles, oxygen can remain trapped in small pockets, allowing smoldering to continue even after CO2 application. The fire appears extinguished when surface flames disappear, but internal combustion persists. Minutes after firefighters move on, flames reignite. The preliminary investigating committee noted water fog was eventually necessary despite electrical hazards. This decision represents a significant escalation. Water conducts electricity. Applying water to energized circuits creates shock hazards for firefighters and short-circuit hazards for equipment. But CO2 has failed to fully extinguish the fire. Foam extinguishers are not suitable for electrical fires. Dry chemical agents would leave residue that could permanently damage instrumentation. Water fog, a fine mist rather than a solid stream, offers a compromise. It cools burning material more effectively than CO2. It penetrates cable bundles more thoroughly. The fine droplets reduce but do not eliminate electrical hazards compared to solid streams. Emergency ventilation fans are brought in to clear smoke, improving visibility and allowing firefighters to reach deeper sections of cable trays. The decision to use water introduces new risks. Shorts increase in frequency as water contacts energized conductors. Control room operators observe additional circuit failures as water application begins. Some failures are temporary. Water creates a conductive path, current flows, then the water evaporates and the circuit recovers. Others are permanent. The surge of current melts conductors or destroys solid-state components. The fire is no longer confined to penetration 5. It has spread to cable trays that connect to the emergency core cooling system. These trays carry signals that control high-pressure injection pumps, low-pressure injection pumps, core spray systems, and containment cooling. The fire threatens the electrical pathways needed to remove decay heat from both reactor cores. The firefighter's task is complicated by the ongoing plant operations. The reactors are shut down, but they still require continuous cooling. Electrical systems remain energized to power pumps and instrumentation. Firefighters cannot simply de-energize everything and flood the area with water. They must balance fire suppression against the need to maintain critical cooling functions. 1:10 to 1:20 in the afternoon. Units 1 and 2 control rooms. Operators observe erratic signals from emergency core cooling system instrumentation. The ECCS is designed to remain reliable through diverse routing. Physical separation of cable runs, different power supplies, independent instrument channels, but multiple. Circuits are now showing degraded or intermittent behavior. The emergency core cooling system for a boiling water reactor includes several subsystems. Core spray injects water directly onto the reactor core from above. High-pressure coolant injection maintains water level using the reactor's own pressure. Residual heat removal provides long-term cooling after the reactor has been shut down. Each subsystem contains multiple pumps, valves, and control circuits. At Browns Ferry, core spray indicators begin displaying anomalous readings. One pump shows running status, but flow indication is 0. Another shows stopped, but electrical current draw indicates the motor is energized. A third pump loses all indication. No status, no flow, no pressure reading. Operators cannot determine pump state from the control room. Residual heat removal pumps face similar problems. RHR is critical during shutdown conditions because decay heat continues to be generated even after control rods are fully inserted. About 4 to 6% of full thermal power persists as unstable fission products decay. This heat must be removed continuously, or core temperature will rise to damaging levels. RHR pumps circulate coolant through heat exchangers, transferring decay heat to the service water system. Unit 1 RHR instrumentation shows multiple failures. Pump discharge pressure readings fluctuate. Heat exchanger outlet temperature sensors lose signal. Flow indicators cycle between 0 and normal. Valve position indicators show contradictory states. A valve appears both open and closed simultaneously, an electrical impossibility suggesting circuit damage. The archival fragment from plant records states, cooling pathways required manual verification due to instrumentation loss. This phrase captures the severity of the situation. Operators can no longer trust remote indicators. They must use alternative methods to confirm that cooling systems are functioning. Containment isolation logic also degrades. Containment isolation valves close automatically if radiation sensors detect abnormal activity or if certain accident conditions occur. The logic circuits for these valves route through the cable spreading room. Loss of these circuits could prevent proper containment isolation or, conversely, cause spurious isolation signals that would complicate plant operations. Main feed water pump controls show intermittent failures in Unit 1. Feed water pumps supply water to the reactor to replace inventory that evaporates into steam. Although the reactors are shut down, some feed water flow may be needed to maintain level until alternate cooling methods are fully established. The numbers tell the scale. Over 1,600 cables will ultimately be found damaged in the fire. 200 control circuits will require complete replacement. This is in a facility designed so that no single initiating event could disable multiple safety systems. The common mode vulnerability created by shared cable routing was not identified during design, construction, or licensing reviews. Operators relay orders by radio to field personnel. Go to RHR Pump 1A. Confirm motor rotation by sound and vibration. Report back. Check valve position at torus spray loop B manually. Verify stem position against indicator markings. Personnel stationed throughout the plant become the operator's eyes and ears, substituting for failed instrumentation. The situation approaches a threshold. If fire spreads to several additional cable trays, shutdown cooling capability could become unrecoverable. The reactors would still be shut down. Control rods are inserted by mechanical springs, not by electrical signals. But removing decay heat would require improvised methods without reliable instrumentation to guide operations. 1:20 to 1:25 in the afternoon. Unit 1 control room. The residual heat removal system indicators fail completely. The control board shows no pump status, no valve positions, no flow or pressure readings. The RHR system is essential for removing decay heat during shutdown conditions. Without it, core temperature will gradually rise as fission product decay continues. Multiple ECCS trains are designed to survive single failure conditions. Redundancy is built into every aspect of the safety systems. If one pump fails, another can take over. If one valve sticks, alternate flow paths exist. If one power supply is lost, emergency diesels provide backup. The design philosophy assumes failures will be random and independent. It does not account for widespread circuit impairment affecting multiple trains simultaneously. The preliminary investigating committee recorded testimony that Browns Ferry approached a condition in which shutdown cooling capability might have been lost. This statement is carefully worded. Approached rather than reached. Might have been rather than was. The phrasing reflects the uncertainty operators faced. Without reliable instrumentation, they could not definitively confirm cooling status. They had to infer function from indirect indicators, temperature trends, pump sounds, valve stem positions observed in the field. Technical analysis shows the margins. Decay heat in a recently shut down boiling water reactor amounts to approximately 4% of full thermal power immediately after shutdown, declining gradually over hours and days. For a 1065 megawatt electric reactor, full thermal power is approximately 3,290 megawatts thermal. 4% equals 132 megawatts of heat that must be continuously removed. If residual heat removal pumps stop, coolant temperature would begin rising at a rate determined by the thermal mass of water in the reactor vessel and connected piping. Initial calculations by TVA engineers suggested that complete loss of shutdown cooling could result in core uncovery within several hours depending on initial conditions. Core uncovery means the water level drops below the top of the fuel rods, allowing them to overheat. Overheating leads to cladding failure and potential fuel damage. The fire's proximity to RHR pump control wiring is documented in cable routing records. Tray sections 11 through 15 all contain RHR circuits. Sections 13 and 14 pass directly over the area where fire is most intense. Heat damage to conductors in these sections affects pump control circuits, valve positioning signals, and instrumentation feeds. The operator's situation is paradoxical. They believe RHR pumps are running. Field reports confirm motor vibration and coolant circulation sounds, but they cannot verify flow rates, cannot confirm heat exchanger performance, cannot monitor for abnormal trends that might indicate developing problems. They are operating with decay heat removal systems in an unmonitored state. If the fire spreads an additional 3 to 4 cable trays westward, it will reach circuits controlling alternate shutdown cooling methods. Emergency procedures provide for use of other systems. Core spray can be operated in a cooling mode. Feed water can be established to maintain level. Even control rod drive hydraulics could theoretically provide some makeup flow. But all of these alternatives require functioning instrumentation to operate safely and effectively. The documented record shows that Browns Ferry remained on the edge of this threshold for approximately 20 minutes. Fire spread was halted before reaching the critical tray sections that would have eliminated all remote shutdown cooling capability. A few additional feet of cable destruction, a few more minutes of uncontrolled flame propagation, and the event would have crossed from a significant fire to a potential core cooling emergency. 1:26 to 1:40 in the afternoon. Throughout Browns Ferry, operators deploy personnel to physically inspect valves, pumps, and alignment markings. Manual verification is intended as a backup method, a fallback procedure used when instrumentation is suspect. It is not designed to be the primary mode of operation during an active emergency with fire-threatening safety systems. The archival quote from TVA operations record states, "Field personnel were stationed at key pump locations to confirm operation by direct observation." This represents a fundamental change in operational mode. Nuclear power plants are designed for remote operation. Hundreds of sensors feed information to the control room. Operators make decisions based on instrument readings, not on direct visual inspection of equipment. Requiring field verification means abandoning the normal operating paradigm. The systems requiring manual oversight include residual heat removal, core spray, torus spray, and suppression pool temperature instruments. Each system involves multiple pieces of equipment distributed throughout the reactor building and auxiliary buildings. RHR pumps are located in separate rooms. Heat exchangers occupied different elevations. Valves controlling flow paths are positioned along pipe runs that span several floors. Communication becomes essential. Operators radio instructions to field personnel. Verify RHR pump 1A discharge valve is full open. Check stem position against indicator markings on the valve yoke. The field technician must locate the valve, access the valve operator, observe the position indicator, and report back. This process takes minutes for each verification. During normal operations, the same information would be available instantly on the control room panel. Suppression pool temperature is a critical parameter during shutdown cooling. The suppression pool, the large torus-shaped water reservoir beneath the reactor, acts as a heat sink. RHR heat exchangers dump decay heat into service water, but some heat also enters the suppression pool through pressure relief operations and other pathways. If pool temperature rises too high, its capacity to condense steam diminishes. Temperature sensors in the suppression pool connect to the control room through cables that route through the spreading room. Many of these sensors have lost signal. Operators must send technicians to read local temperature gauges installed at various points around the torus. The technicians report readings by radio. Operators plot these readings on paper to track trends. What was automatic is now manual. What was instant is now delayed. What was continuous is now intermittent. Instrumentation losses force operators to approximate system states. If RHR flow cannot be measured directly, operators estimate it based on pump discharge pressure, pump motor current, and coolant temperature change across the heat exchanger, assuming those readings are available and trustworthy. If valve position cannot be confirmed remotely, operators assume the valve responded to its last control signal and remained in that position. These assumptions carry risk. A valve could have failed mid-stroke, a pump could have tripped, an instrument reading could be false. The radio becomes the lifeline. Control room operators maintain continuous communication with personnel at RHR pumps, at core spray initiation valves, at torus spray distribution headers, and at suppression pool temperature monitoring points. Each person becomes a human sensor, reporting observations that substitute for failed instrumentation. The human element replaces the electronic network that fire is destroying. This mode of operation is sustainable for minutes or hours, but not for days. Personnel fatigue. Communication becomes garbled. Handwritten logs accumulate errors. The longer the situation persists without reliable remote instrumentation, the greater the likelihood that critical information will be missed or misinterpreted. Browns Ferry operators must maintain manual coordination while simultaneously dealing with an active fire that continues to threaten additional circuits. Cooling continues only through confirmed manual alignment. Instrumentation is no longer trustworthy. The control room has become a coordination center rather than a monitoring station, directing human observers rather than reading electronic signals. 1:40 to 3 o'clock in the afternoon. Cable spreading room. Water fog suppresses open flames after carbon dioxide proves insufficient. The decision to use water on energized electrical circuits is not taken lightly. Water conducts electricity. Firefighters face shock hazards. Equipment faces short-circuit damage. But fire spread has continued despite CO2 application, and no other option remains effective. The fire brigade adjusts nozzles to produce fine fog rather than solid streams. Fog droplets disperse in the air, cooling surfaces and displacing oxygen without creating continuous conductive paths from hose to ground. The technique reduces but does not eliminate electrical hazards. Firefighters wear insulated gloves and boots. They maintain distance from energized equipment. They apply water in short bursts, observing the fire's response between applications. TVA's post-incident assessment documents the outcome. The fire was brought under control after application of water fog, though electrical damage was extensive. This statement confirms both the effectiveness of water and the cost of using it. Control is achieved. Damage is accepted. Emergency ventilation fans are brought to full capacity. Smoke clears gradually, revealing the extent of cable destruction. Entire sections of tray are charred black. Insulation has burned away completely in some areas, leaving bare copper conductors exposed. Other sections show partial damage. Heat-softened jackets, discolored insulation, conductors fused together into lumps of melted plastic and metal. The scale of the event becomes clear. 7 hours of active firefighting in a facility designed for complete fire suppression within minutes. Flames spread, threatened systems across 2 entire reactor units from a single ignition point. Over 1,600 cables damaged, 200 control circuits destroyed completely, requiring full replacement rather than repair. Design assumptions about fire behavior in nuclear plants did not anticipate this outcome. Regulations in 1975 focused on fire prevention rather than fire propagation. Cable insulation materials were not required to be flame retardant. Penetration seals were not required to be fire-rated. Cable trays were not required to have fire barriers between trains. Detection and suppression systems were minimal in areas like cable spreading rooms that did not contain obvious ignition sources. With flame spread halted, cable impairment stabilizes. New circuits are not being damaged. Existing damage stops progressing. Operators can begin to assess which systems retain function and which require alternate methods. The shift from emergency response to recovery mode begins. Both reactors remain safely shut down throughout the event. Control rods inserted automatically when the reactor scram signal was initiated, shortly after operators recognized the extent of circuit failures. The rods are held in place by mechanical springs, not by electrical power, so their position is not dependent on cable integrity. The reactor cores are subcritical. The chain reaction has stopped. The challenge is removing decay heat, not controlling reactivity. But the path to safe shutdown was closer to the edge than design assumptions predicted. The NRC's 1976 report assessing Browns Ferry states, "The Browns Ferry fire was the most serious U.S. nuclear power plant incident to date in terms of potential hazard." The phrasing reflects the conditional nature of the outcome. Actual radiological release was zero. Fuel damage did not occur. Containment integrity was maintained. Yet the potential existed for a more serious event if fire had spread further, or if operators had been unable to maintain core cooling using degraded instrumentation and manual field verification. The incident demonstrates a vulnerability that regulatory frameworks had not addressed: electrical fire as a common mode failure mechanism. Browns Ferry forces a re-examination of assumptions about independence, redundancy, and defense in depth when electrical systems create unexpected coupling between supposedly separate safety trains. March through October of 1975. Browns Ferry Nuclear Plant. Engineering teams begin the assessment. They must document every damaged cable, trace every failed circuit, and determine what can be repaired versus what must be replaced. The scale is enormous. The cable spreading room contains thousands of conductors. Identifying which ones burned, which ones were heat damaged but might still function, and which ones are intact requires methodical inspection. Final counts show 1,600 cables impaired to some degree. Of these, 200 control circuits require complete replacement. Complete replacement means pulling new cable through conduits, rerouting through trays, terminating connections at both ends, and testing for proper function. The work will take months, but replacement alone is not sufficient. The fire revealed fundamental design vulnerabilities. Polyurethane foam penetration seals allowed fire to spread from room to room. Unprotected cable trays provided continuous fuel pathways. Lack of fire barriers between redundant safety trains meant that one fire could disable multiple systems simultaneously. These vulnerabilities exist not just at Browns Ferry but at nuclear plants throughout the United States. TVA implements immediate corrective actions at Browns Ferry. Fire-rated penetration seals replace polyurethane foam at all major cable penetrations. These new seals use intumescent materials that expand when heated, forming a char layer that blocks flame propagation. They are tested and certified to withstand direct flame exposure for specified durations, 1 hour, 2 hours, 3 hours, depending on application. Cable routing undergoes extensive redesign. Where possible, redundant safety system cables are physically separated. Different trays, different rooms, different elevations. Where complete separation is not feasible, fire barriers are installed. These barriers consist of fire-rated wraps or coatings that protect cable bundles from flame spread. The principle is to prevent a fire in one train from affecting another train long enough for operators to detect the fire and take corrective action. Mandatory fire detection and suppression systems are installed in all cable spreading rooms and other areas containing significant concentrations of safety-related circuits. Heat detectors, smoke detectors, and automatic water-based suppression systems provide early warning and rapid response. The goal is to detect ignition within seconds and suppress it within minutes, preventing the kind of spread that occurred on March 22nd. Enhanced operator training addresses fire response procedures. Operators learn to recognize cable fire indicators, multiple circuit failures in related systems, smoke reports from specific areas, degradation of instrumentation rather than component failures. They practice manual verification procedures and alternate shutdown methods that do not rely on the circuits most likely to be affected by fire. The archival fact from TVA records states, "Extensive redesign of cable separation was implemented." This phrase understates the scope of work. Redesign means reanalyzing every cable routing decision made during original construction, identifying vulnerabilities, and implementing physical modifications to plant systems. It means spending millions of dollars and thousands of worker hours to correct deficiencies that were not recognized as deficiencies when the plant was built. But the work at Browns Ferry is only the beginning. The Nuclear Regulatory Commission must now determine whether similar vulnerabilities exist at other plants and what corrective actions should be required industry-wide. This reconstruction becomes the cornerstone for new national fire protection standards that will transform nuclear plant design and operation. 1975 through 1977 and beyond, Nuclear Regulatory Commission headquarters. Regulators face the implications of Browns Ferry. The event exposed weaknesses in fire protection that existing regulations did not address. The response must be comprehensive, affecting every operating nuclear plant in the United States and every plant under construction. The NRC issues new requirements under Title 10, Code of Federal Regulations, Part 50, Section 48, and creates Appendix R, Fire Protection Program, for nuclear power facilities operating prior to January 1st, 1979. These regulations establish mandatory standards that go far beyond previous guidance. Key requirements include mandatory alternative shutdown capability. Plants must demonstrate they can achieve and maintain safe shutdown conditions even if fire destroys all cables in the most critical fire area. This means identifying alternate systems, establishing procedures, and ensuring operators are trained to implement those procedures without relying on normal instrumentation. Rated fire barriers become mandatory between redundant safety trains. If cables for Train A and Train B of the emergency core cooling system must share a common area, they must be separated by barriers that can withstand fire for a specified time, typically 3 hours. Barriers are tested to standards developed by organizations like Underwriters Laboratories and the American Society for Testing and Materials. Improved fire detection and suppression systems are required throughout the plant. Areas containing safety-related equipment or cables must have automatic detection that alarms in the control room and activates suppression systems. Suppression systems must be designed to control fire without causing unacceptable damage to safety equipment. This leads to widespread installation of automatic sprinklers, deluge systems, and gaseous suppression systems using halon or carbon dioxide. Industry-wide redesign of penetration seals begins. The foam seals that allowed fire to spread at Browns Ferry are systematically replaced with fire-rated seals at every nuclear plant. The NRC issues generic letters and bulletins directing licensees to inspect existing seals, test them if possible, and replace any that do not meet new fire-resistant standards. The regulatory transformation extends beyond physical modifications. Fire protection becomes a permanent part of plant licensing and oversight. Every plant must maintain a fire hazards analysis that identifies potential fire scenarios, evaluates their consequences, and demonstrates adequate protection. Fire drills and training become routine. Fire protection engineers join plant staffs as permanent positions, not just consultants brought in during construction. The NRC's 1976 report on Browns Ferry states unequivocally, "The Browns Ferry fire was the most serious U.S. nuclear power plant incident to date in terms of potential hazard." This assessment drives regulatory urgency. Browns Ferry did not result in fuel damage, did not cause radiological release, did not injure workers or the public, but it came close enough to possibilities that the NRC determines comprehensive action is required. The event permanently alters nuclear safety culture. fire is now recognized as a credible initiating event that must be analyzed with the same rigor as loss of coolant accidents, seismic events, or external floods. Design basis documents for new plants include detailed fire protection analyses. Operating plants undergo backfits to meet new standards. The changes affect every aspect of plant design. Cable trays are rerouted. Walls are added to create fire compartments. Coatings are applied to structural steel to prevent heat-induced failure. Emergency lighting systems are upgraded to function during fire conditions. Alternative shutdown panels are installed outside the main control room to provide backup control capability if the control room becomes uninhabitable due to smoke or heat. The work takes years and costs hundreds of millions of dollars across the industry. But the alternative, operating with the vulnerabilities Browns Ferry revealed, is unacceptable. The potential consequences of common mode cable fire affecting multiple safety systems are too severe to ignore. The lessons of Browns Ferry endure in every US nuclear plant today. They are written into cable routing diagrams that show physical separation between redundant trains. They appear in fire-rated penetration seals that block flames spread at every boundary. They exist in emergency procedures that guide operators through fire response and alternative shutdown. They persist in code requirements shaped directly by a single candle held near polyurethane foam on the afternoon of March 22, 1975, an ignition that changed an industry.